Welcome to the deep dive. You've shared your sources, and we are ready to take a truly massive look at the underlying physics of reality.
Yeah, this one is big.
Today, we're exploring periodic motion, this fundamental invisible architecture that governs everything from the color of the light hitting your eyes to, the way we define musical harmony.
This really is a deep dive into vibration, but across all scales.
Hmm.
Our sources today are a fascinating mix. We have everything from classic foundational physics textbooks explaining, simple harmonic motion,
The basic.
all the way up to advanced academic papers on acoustics and even the quantum mechanics of molecular bonds.
So our mission is pretty specific. We need to clearly differentiate the two key properties of any oscillation, that's amplitude and frequency.
And then trace them.
Exactly. Trace those concepts from the macro world like sound and light all the way down to the microscopic world of, molecular chemistry.
And by the end, you'll really start to see the universe from top to bottom as one connected, vibrating system.
Okay, let's unpack this. When we talk about anything that moves back and forth or up and down over and over, these two properties define it completely, but they are absolutely distinct.
Completely.
Let's start with the easiest one to visualize, I think. Amplitude.
Amplitude, yeah, it's usually designated by the letter A, and it's essentially the wave's size.
Its size, okay.
It is the maximum displacement from the equilibrium position. So if you picture a pendulum just hanging still.
That's equilibrium.
Right, and how far out to the side it swings before it turns back, that maximum distance, that's the amplitude.
So amplitude describes the wave's intensity or its strength. If I'm describing the power of the wave, I'm talking about A.
Precisely. And that takes us immediately to energy.
Right.
Amplitude is measured in units of displacement, meters or feet. But its real significance is that it relates directly to the total mechanical energy in that system.
So think about that moment the pendulum reaches its peak.
Yeah, at its peak amplitude, its kinetic energy is zero, and its potential energy is absolutely maximized. It's just ready to convert back to motion.
A bigger swing, a bigger wave means more stored energy.
Exactly.
I found a great analogy in one of the sources for water waves. Say you have a water wave with an amplitude of 3 feet.
Okay.
That tells you the distance from the average water level up to the crest is 3 feet. That wave is storing way more energy than just a little 6-inch ripple.
Which brings us to its counterpart, frequency. This describes the rate, how often the event repeats itself.
So if amplitude is the size of the swing, frequency is the speed of the swing.
You got it.
And the measurement for frequency is incredibly intuitive, isn't it? Hertz. Hertz.
Which just means cycles per second. Sometimes you'll see RPM, revolutions per minute, especially in engineering.
Right, and 60 RPM is just 1 hertz.
But conceptually, it all boils down to a very simple relationship. The frequency, we'll call it for dollars, is just the reciprocal of the period. $T.
And T is the time it takes for one complete cycle.
That relationship equals 1 over $2. That's the key. So if you're trying to calculate the frequency of something simple, like a machine completing, say, 10 cycles in 1 minute.
You just convert that minute to 60 seconds.
And you get 10 cycles per 60 seconds, which gives you a frequency of about 0.17 hertz.
That example makes it so clear that frequency is strictly about the rate. It's totally independent of how far that thing is swinging.
Right. So to kind of sum up this first part for you listening, amplitude is the energy, the intensity, the sheer scale of the vibration.
And frequency is the rate, the speed, the identity of the phenomenon, the pitch, the color, the chemical signature.
So now we take those fundamentals and apply them to propagation to waves actually moving through space.
And here, frequency gains this inverse relationship to wavelength, which we call lambda.
Right. The speed of the wave, Wöhler rule, is the product of frequency and wavelength. So that means Wöhler equals vol divided by lambda.
And that brings up a really crucial insight I found in our sources. What happens when a wave moves from one material into another?
That is where it gets really, really interesting. Because the wave's frequency remains constant.
Even when the other things change.
Even as the wavelength and the speed change, think about light refracting. When light moves from air into a piece of glass, it slows down.
Okay.
And its wavelength actually shortens. But the light's frequency, its color identity, that doesn't change.
Wait, hold on. So if I put a diamond into water, the speed of the light changes, the wavelength of the light changes, but the actual color, the frequency, is fixed by the atoms that emitted it.
Yes.
That identity is locked in no matter the medium. That's wild. It makes frequency feel like the ultimate fingerprint of the vibration.
It truly is. It's inherent to the source. Now let's apply this to sound waves.
Okay.
Sound propagates as a mechanical wave of pressure and displacement. And the speed, Vilers, is more or less fixed by the air density and temperature.
And since dollars is fixed, the frequency determines the pitch. So a higher frequency, more cycles per second, means a shorter wavelength and a higher pitch. A lower frequency means a longer wavelength and a lower pitch.
Which is why our ears can pick up that whole range from about 20 hertz, which is that deep bass rumble,
All the way up to 20,000 hertz, that high piercing whistle.
Meanwhile, the amplitude of that same sound waves determines its intensity, what we perceive as its loudness.
A louder sound just requires more physical energy to push the air molecules further, a larger displacement.
The guitar example from the source material is perfect for this.
Yeah, if you pluck a string with tremendous force, you increase its initial amplitude. It's louder.
But if you want to change its pitch,
You have to change its frequency. You press the string down, shorten its effective length, which forces a shorter wavelength and a faster vibration.
okay, now let's jump. Let's go up in frequency by orders of magnitude and look at light.
Visible light.
It's an electromagnetic wave. Fundamentally the same phenomenon as radio waves or microwaves or gamma rays. They only differ in their frequency and wavelength.
And just as frequency determines pitch in sound, frequency determines color in light.
And we're talking about incredibly fast vibrations here. Red light, which has the lowest frequency of the visible spectrum, is around 400 terahertz.
That's 4 times 10 to the 14th hertz, just an insane number.
And we perceive the color changing as that frequency basically doubles up towards violet light, which is around 800 terahertz.
And beyond those extremes, you get into the invisible stuff, infrared and ultraviolet. Because light in a vacuum travels at a constant speed, 12.
The formula simplifies to photio equals study dollar divided by lambda.
Measuring these speeds is a feat in itself. You can't just stop and count these cycles.
Not at the gigahertz range, no.
For low frequencies, the sources mention this clever trick. Instead of counting how many events happen in 1 second, you remember the exact time it takes for, say, 100 events to occur.
Right, and this avoids what's called gating error. It's just the imprecision of trying to line up your start and stop times perfectly.
But for the really fast stuff, up to 100 gigahertz, we need frequency counters.
Using highly precise quartz time bases, yeah. And beyond that, we have to rely on indirect techniques. The most prominent one is called the heterodyne method.
I love this trick. It's so smart.
It is.
Since you can't count the unknown superfast signal, you mix it with a known reference frequency.
It's like having two cars driving at, say, 100 miles per hour, but one is going 101.
You can't really see the absolute speed difference just by looking, but if you measure how far apart they're pulling every minute.
You can calculate that tiny difference.
Exactly. The unknown signal and the known signal create a low-frequency difference wave, or a beat signal, that is slow enough to measure precisely.
And once you measure that beat frequency, you can just back calculate the original unknown high frequency. It's a classic physics workaround.
Speaking of things our ears measure, let's pivot to music. This is where the physics we've discussed becomes, a shared human experience.
Yeah, music depends entirely on the creation of standing waves.
Okay.
If you take a standard stretched string of length, dollars, like on a violin or a piano, with fixed ends, the simplest, longest wave it can sustain is the fundamental frequency, fifth all 1.
And the wavelengths for that fundamental mode is actually twice the length of the string.
Right, but the magic, the complexity, comes from the higher modes of vibration that exist at the same time. We call them harmonics.
So the string doesn't just vibrate at fuff dollars?
No, it also vibrates at 2 times stuffed dollar, 3 times stuffed dollar ball, 4 times soft dollars, so on. The frequency of the nth mode is just n times the fundamental.
Yep.
We also call these overtones.
And this rich combination, this superposition of the fundamental tone and all those higher harmonics.
That's what determines the instrument's tonal quality. It's timbre.
Timbre. It's the color or the flavor that makes a clarinet sound different from a violin playing the exact same note.
The same fundamental frequency, yeah.
That's why technique matters so much. If you play a guitar string closer to the bridge, you naturally suppress the fundamentals node while emphasizing the higher harmonics.
And you get a sharper, brighter sound.
But if you pick closer to the middle, the lower, more mellow harmonics dominate.
You can even hear this in basic waveforms. A pure sine wave, which is only the fundamental, is very mellow and soft.
Whereas a square wave, which is rich in all these odd-numbered harmonics, sounds much brighter, almost buzzy.
And we know from the sources this harmonic content isn't static. The acoustic signature of an instrument changes dramatically during the note's attack phase, the very beginning.
That rapid change in the balance of harmonics is a huge part of an instrument's identity. It's why those interferograms of violins show these wildly complex vibrational patterns.
Exactly. It all determines the resonant structure.
So if physics is creating this rich tapestry of sound, why do certain combinations sound inherently good to us?
This brings us to that aha moment the ancient Greeks stumbled upon. They found that simple ratios of frequencies.
The octave, which is 2 to 1, the perfect fifth, 3 to 2, the fourth, 4 to 3.
They found these were inherently pleasing, consonant.
And the physical explanation for this is just, it's beautiful.
It really is. When you combine frequencies that share these simple integer ratios, the resulting composite waveform is time-independent.
Which doesn't mean it's static. It means the complex pattern of the combined wave is highly repetitive and predictable.
So how does our brain process predictable as pleasing?
I was just about to ask.
Well, our auditory system, specifically the basilar membrane inside the fluid-filled cochlea, it's like a physical Fourier transformer.
It breaks sound down into its component frequencies.
Yes. And when the incoming signal is highly consonant, when the waveform is simple and perfectly repeating, it creates these stable, clean-standing wave patterns on that basilar membrane.
In other words, the signal isn't messy or chaotic. It's exceptionally easy for the brain to process.
Precisely. That effortless processing of a clean, stable physical pattern is what we neurologically perceive as consonant, as pleasure.
And dissonant intervals would create chaotic shifting patterns that take much more effort to decipher.
Exactly. So we've gone from sound waves you can see on a membrane to light waves measured in terahertz.
Mm.
Now let's jump to the truly microscopic level.
The vibration inside molecules. This is where periodic motion literally defines chemistry.
And we are talking about speeds that are nearly unimaginable. Typical molecular vibrational frequencies range from 10 trillion hertz
That's 10 to the 13.
up to around 100 trillion hertz.
100 trillion times per second. I mean, your body is fundamentally composed of molecules that are vibrating at this speed constantly.
Yeah, molecular vibration is the periodic motion of atoms relative to one another within the structure, and it's always ensuring the overall center of mass of the molecule stays fixed.
And just like a guitar string vibrating in defined harmonics, these complex molecules don't just jiggle randomly.
No, they perform these coordinated dances called normal modes. These are independent, simultaneous vibrations of different parts of the molecule.
And the geometry of the molecule dictates how many modes it has. For a nonlinear molecule with not atoms, it has 3 nanomoles minus 6 normal modes.
Right, that number accounts for the 3 degrees of translational freedom and 3 degrees of rotational freedom for the whole molecule.
If you look at just a simple part of a molecule like the CH2 group, it doesn't just stretch.
It has a whole repertoire of movements.
Symmetric stretching, asymmetric stretching, scissoring, rocking, wagging, and twisting.
And each of those motions is a distinct vibrational mode with a distinct frequency.
To understand these incredibly fast quantum motions, we often fall back on a classical analogy.
The simple harmonic oscillator. We treat the atoms like masses connected by perfect springs that obey Hooke's law.
Right, and the frequency of that vibration depends on two things. The force constant, the corrodollar, which is the stiffness of the spring,
Or the chemical bond strength.
and the reduced mass, mu.
The reduced mass is such a critical concept, you can't just add the masses of the two atoms like carbon and oxygen.
No, you have to account for their relative motion around that center of mass.
And reduced mass is what lets us model that two-body problem as a single body oscillating around a fixed point. It's essential for getting the frequency right.
And this vibration gets excited when the molecule absorbs a quantum of energy, delta E, that exactly matches the frequency that one of its normal modes.
According to the equation, delta E equals h nu.
And since these molecular frequencies are so high, they require energy that corresponds precisely to the infrared region of the electromagnetic spectrum.
Which is why infrared spectroscopy is such a powerful tool in chemistry. By shining IR light on a sample and seeing what frequencies get absorbed, you are literally mapping the vibrational fingerprints of the chemical bonds inside.
But we also have to acknowledge that those springs aren't perfect.
Right. Real bonds exhibit aharmonicity. They don't perfectly follow Hooke's law, especially when they're stretched hard.
And this deviation is what allows the molecule to absorb multiple quanta of energy at once. We call them overtones.
Though the energy needed for these overtones progresses unevenly, and eventually it can lead to the bond actually breaking, dissociation.
So we have come full circle. We've established that amplitude is the scale of the physical wobble. It defines energy and intensity. whether that's the loudness of a note or the brightness of a star.
And frequency is the speed of the wobble. It defines identity, the pitch of a sound, the color of light, or the unique vibrational signature of a chemical bond.
And by understanding the physics of frequency and standing waves, we've revealed why music resonates so deeply with us.
Our brains are not just passively listening. They are optimally engineered to efficiently process those stable, consonant wave patterns, and they interpret that ease of processing as pleasure.
It shows that vibration isn't just a scientific concept, it's really the source of sensory meaning.
That's a great way to put it.
So here's a final thought for you. Given that our pleasure response is hardwired to process simple, stable harmonic ratios, like the octave or the fifth, and that many non-Western musical traditions use microtonal scales with far more complex irrational frequency ratios, what might happen if we deliberately engineer music that uses slightly dissonant or complex ratios to challenge the brain's processing efficiency? Could the systematic introduction of structured complexity, or even, say, controlled harmonic chaos, unlock entirely new dimensions of auditory experience or cognitive response?
That's a fascinating question.
Think about that the next time a song makes you feel something truly unexpected.